Today, we're going to talk about something kind of wild. The elegant and honestly terrifying math that's hiding behind the world's biggest disasters.
So picture the most chaotic thing you can think of, like a pandemic sweeping the globe or a stock market just collapsing. We usually just write these off as random, right? Unpredictable acts of nature. But what if they're not random at all? What if, buried deep inside all that chaos, there are actual, precise, mathematical rules?
And yeah, that's exactly what we're digging into today. It turns out that things like calculus and probability, they're not just stuff you fall asleep to in a textbook. They are literally the hidden language of catastrophe. And they give us this incredible lens to see and maybe, just maybe, even predict what seems completely unpredictable.
All right, so where do we even begin with something this big? Well, let's start with an experience we all share, the spread of a disease and the math that tried to map out its path. The main tool for this job is something called a differential equation. I know, it sounds super intimidating, but the core idea is actually pretty straightforward. It's just a way to describe how things change over time. Think of it as the language of motion, of growth, and crucially for our story, the language of spread. A perfect example of this in action is the SIR model. It's simple, really. It just splits everyone into 3 buckets: susceptible, infected, and recovered. By using those differential equations, scientists could model how people moved from one bucket to the next, which let them predict when an infection might peak. But here's the really powerful part. It showed how interventions could flatten that curve. It took pure chaos and turned it into something calculable.
But here's what's so wild. This math isn't just for diseases. Not at all. It works for almost anything that spreads. Think about it. A piece of misinformation going viral online. That ripple of fear that causes a market crash. Even just a fashion trend that's suddenly everywhere. They all follow these same fundamental mathematical rules.
Okay, so we've talked about things that spread, things that grow over time. But what about things that just break? All at once, a single catastrophic failure. For that, you need a totally different kind of math. We're moving from modeling a continuous flow to calculating the odds of a single roll of the dice.
So let's jump into that. We're shifting gears now, from the invisible spread of a virus to the very real, very physical risk of something collapsing.
So how on earth do you figure out the risk of something that hasn't even happened yet? Well, you run something called a Monte Carlo simulation. And it's kind of like having a supercomputer that can roll the dice millions or even billions of times. It tests every possible tiny stress, every single variable, every little weakness, just to find that 1 in a billion scenario where everything goes wrong.
And this isn't just theory. Engineers use this stuff every single day to build our world. You know the safety margins on a rocket coming back to Earth? That's calculated. The strength of a skyscraper in an earthquake? Calculated. This math is like this silent guardian, working in the background, making sure all this complex stuff we rely on just doesn't fail.
And a lot of the time, this is the number they're shooting for, 1 in a million. For critical things, they want the probability of a total disaster to be less than 1 in a million. And that really brings it home, doesn't it? Safety isn't just a vague feeling. It's a number that's been calculated with an incredible amount of precision.
All right, so we've got the math for things that spread and the math for things that break. But what about nature? What about the wild, beautiful, raw chaos of a natural disaster? For that, we need to talk about fractals. And this is where things get really cool and a little mind-bending. Fractals are the geometry of chaos, of things that aren't nice and smooth. The key idea is something called self-similarity. It basically means a pattern repeats itself over and over, no matter how far you zoom in or zoom out. And once you know what to look for, you see them everywhere in nature. That jagged line of an earthquake fault, that's a fractal. The way a wildfire branches out, fractal. Even the swirl of a hurricane. And here's where it all starts to click together. You can take the fractal data from, say, a fault line and feed that into one of those probability simulations we were just talking about. Suddenly, your risk assessment gets a whole lot smarter. Okay, so let's recap. We've got differential equations for how things spread, we've got probability for when things might break, and we've got fractals to understand the patterns in nature. So, what does it all add up to? What does this mean for the future? Well, it means we're on the cusp of a totally new kind of foresight, an era where all these different mathematical tools don't just sit in their own little boxes, they talk to each other. By mashing all this up with AI and big data, we can start building models that are powerful enough to really get a handle on huge problems like climate change or even massive cyber attacks. And really, that's the bottom line here. This isn't just some abstract math problem. Understanding the calculus of catastrophe gives us a real shield against the chaos. It lets us build better, stronger, more resilient systems. It literally helps us save lives. Knowing the pattern is truly our best defense.
But that leaves us with one last really big question. As we get better and better at calculating these disasters, as our foresight gets more powerful, the problem stops being about the math and starts being about morality. If we can see these things coming, what do we choose to prevent? With limited time and money, who and what do we decide to save? And that's something worth thinking about.